lesson is going to be all about angle relationships inside of circles. And what better way to get started with that than just down and dirty with a couple of theorems. We're going to do quite a few theorems today, and I really like what I've been doing recently where I've been giving you more of a abbreviated version of the theorem instead of boring you in the technical jargon. I feel like that's a little bit more helpful. But anyways, this is the tangent and inscribed chord theorem. And so if we draw a circle here, and say we also have a tangent connecting to that, or going through that circle, right? And a tangent intersects at one point. And that point where it intersects, we're going to have a chord that intersects that too. Notice here that we now have formed two angles. We have angle 1 right here, and right next to angle 1 we have angle 2. All right. And then we also have this left side of this circle, and I highlight the right. And we also have the other side of the circle. There we go. All right, so we have angle 1 and we have angle 2, and we have this blue arc and we have this red arc. And in order to complete what we're going to do here, we need to have a couple of points listed. So that intersection point where the tangent meets this chord is going to be A. The top of the chord will be B, and then to differentiate between our two arcs, we need a C over there. And what we're going to find is that the measure of each one of these angles is actually related to the arcs they're connected to. So we're going to start with the measure of angle 1. And the measure of angle 1 is actually going to be equal to 1/2 the measure, so I need a blue here, the measure of arc ACB. Oops, I did the wrong arc. No, I did it. I did the right arc. Yep, the measure of ACB. On my notes I'm referencing, I did the wrong arc, but this is the correct arc. And then the measure of arc 2 here in blue, or angle 2 here in blue, is also going to be 1/2 of the associated red arc. So that's going to be the measurement of arc AB. So the angle is half the measurement of the arc. And why don't we go ahead and put that to use right away. So I'm going to draw two circles here. And each one of these circles is going to have a red section. And I want to find the measurement of the red section. So there's the red section on that one. So we want to find the angle measurement of angle 1. And the associated arc is 130 degrees. And while you think about that, we're going to go ahead and draw the second circle right down here below it. This interior angle right here is going to be 125 degrees. And we want to find this red section right here. There we go. So we'll do this top one first to find the angle measurement. We know that the measure of angle 1 is going to be half of the associated arc. And just for some clarity's sake, we'll plug an A and a B in right here. So that's going to be 1/2 of arc AB. And so the measure of angle 1 is actually going to be equal to 1/2 of 130 degrees, which is equal to 65 degrees. Now, we want to find the measurement of this red arc here. We'll throw down some letters on there. So we got K and L is going to be our chord, and then since this is a larger arc, we need to have J, the major arc. And we know that 125 degrees is equal to 1/2 of our measurement of our larger chord, so K, J, L. We're going to multiply 2 on both sides. We're going to take 2 times 125 degrees, and that's going to equal our measurement, which is equal to 250 degrees. So pretty straightforward process there. Real quick, I want to let you know something. If I draw some circles here, that's a diamond. There's another circle, another circle. All right, this is completely different. If I draw some lines that intersect these circles, there's only, so many places these lines can intersect. They can intersect on the circle. They can intersect, oops. Just messing up all sorts of things today. So 2 lines can intersect on the circle, they can intersect in the circle, or they can intersect, out. That's hard because we want them to both go through the circle. So it's kind of a tricky angle you have to approach these at. There we go. Or they can intersect outside of the circle. So those are the only 3 places that 2 lines going through circles can intersect at. And the reason why we want to know that is we're going to apply that now to a couple of theorems. So this first theorem, 10.15, is going to be the angles inside the circle theorem. And to set up this theorem, we're going to need a circle, of course. And we're also going to need to have 2 chords that intersect inside the circle. All right, right away when you see 2 lines intersecting, you should be thinking of vertical angles, right? So that angle and that angle are going to be congruent, and we'll call those angle 1. And then this top and this bottom are also going to be congruent. That's going to be angle 2. We need to throw down some points where these chords intersect the edge of the circle. So we're going to have A, B, C, and D. Arc AB, we're going to highlight in this bright blue color. Arc CD, we're going to highlight in this nice green color. And we're going to leave AC and BD both black. And so the measurement of angle 1 is going to actually equal 1/2 the measurement of arc AB plus the measurement of arc CD. So this angle 1 right here, both of them are equal to 1/2 of AB plus CD. And the measurement of angle 2 is going to equal 1/2 of the measurement of arc AC, so that's this arc right there, plus the measurement of arc BD. All right, and we're going to go ahead and now see what happens if we have angles outside of the circle. So why don't I just go ahead and move this circle right up here. There we go. And we're going to go ahead and keep this other theorem right below it. And this is going to be the angles outside the circle theorem. And we're going to have 3 possibilities for angles outside of the circle. So our first possibility is if we have a secant line like so, and that doesn't go outside the circle. Nice job. So we have a secant line like so, and then we have a tangent line like that. So that is option number 1. And we're going to go ahead and throw down some marks on this. So that's going to be A, that's going to be B, and this is going to be C up here. Arc AB, once again, is going to be this nice blue color. And arc BC is going to be this nice green color. All right, so that's option 1 where the circles can intersect, and we're going to find it's going to have the same formula for all 3 options. I just want you to be aware of the different options here. All right, option 2 is we have 2 tangent lines intersecting. So it kind of looks like Pac-Man eating a little power-up pellet. This is going to be angle 2, and we're going to use some different letters on this one. So we're going to use P, R, and Q will be out here. PR is going to be our blue one. So we're always going to keep our smaller arc, our minor arc, the blue one, and we're going to keep our major arc, the green one. And then finally, we can have 2 secant lines. And so that's going to look like so. This is going to be, of course, angle 3. And we're going to label this guy with W, X, Y, and Z. WZ is going to be our blue chord, or sorry, our blue arc, and XY is going to be our green arc. Now, each one of these have the same exact formula. It's going to be the measure of angle whatever, angle 1 in this case, is equal to 1/2. Then we're going to take the bigger arc, the green one, the measure of BC, and subtract from it the measure of the smaller one, AB. The reason why we're taking the bigger one first is if we take the smaller one first, we'll get a negative number, and you can't have a negative angle. So you just take the big one, subtract the little one, arc that is, 1/2 that, and that is a measurement of the angle. So it's the exact same formula as our inside the angle theorem, except instead of having a plus, we're going to have a minus. So over here, we're going to have the measure of angle 2 is equal to 1/2 times the measurement of PQR minus the measurement of PR. And then finally, the measurement of angle 3 is going to equal 1/2 the big arc, XY, minus the smaller arc, WZ. So now that we have that information, why don't we put this to good use in a couple of examples? So we're going to have 2 circles. One's going to use angles inside, and one is going to use angles outside. And on both of these, our goal is to find X. So we got J, M, L, and K as our endpoints there. X is going to be this large obtuse angle here. JM is equal to 130 degrees and KL is equal to 156 degrees. And while you do some subtraction and, or sorry, some addition and halving, I'm going to draw another circle over here. That's not a circle. And so we're going to have a tangent line up here. This is going to be C and then D. And then we're going to have another ray going through like so. And we want to find this angle measurement inside here, angle C, which is X. And then this arc here is 76 degrees. And this other arc over here is 178 degrees. So to find X on this first one, we know that X is going to equal 1/2 the arcs added together. So that's going to be 130 plus 156, which is going to be equal to 1/2 of 286, which is equal to 143 degrees. And if we have an angle outside of our two circles, we know X is going to equal the difference of the two. So we're going to take 178 minus 76. So that's going to be 1/2 of 102, which means X is equal to 51 degrees. All right, so we have just a little bit left to go here. We got to first talk about a circumscribed angle. And a circumscribed angle is an angle whose sides are tangent lines. So if we draw a circle here, this is going to look like the Pac-Man, right? So we got two lines that are tangent and they intersect down here. And so this angle, angle 1, is going to be a circumscribed angle. And of course, I'm not going to introduce a new definition without associating a theorem with it. So we have theorem 10.17, which is going to be the circumscribed angle theorem. And so if we draw a circle here, and then draw a circumscribed angle and give it some measurements. So we got A, that's a D. We got A, we'll put D down here, and then we have C over here. All right, and then the measurement of this circumscribed angle is actually equal to 180 minus the measure of the central angle that intercepts the same arc. So if we have our center here, B, this is going to be the central angle that intersects both of those. And so the measurement of angle D is going to equal 180 minus the measurement of angle B. And with that information, I want to find X once again on two last examples. First example is going to be pretty straightforward here. And so we're going to just complete that one in its entirety first. And so there's our center C. We have A and B up here, and we want to find the measurement of angle D, which is also going to be our X. And angle C is equal to 130 degrees. So we know X is going to equal 180 minus the measurement of angle C. So that's going to be 180 minus 130, or X is equal to 50 degrees. All right, this last example gets pretty complicated. So we have our circle here. One tangent line is way down here, and the other tangent is going to be up here. And then we're going to be concerned about, oops, I need to redraw that line there. Is this angle over here All right, and then our center is right here. So our center is going to be G. We got E, J, and F over here, and then H chilling over here. Angle H is actually equal to 30 degrees. And J is equal to X. And we actually have to go back to the last lesson that we just did when we talked about angles, some angle relationships in circles. We know that this is all going to be correlated. So if this guy right here is X, we know that the angle, this interior angle, is going to be half of its associated arc. So we know that EF is equal to 2X. And because this is in one half of a circle and the other half is over here, we know that the other side of the circle, sorry, I'm going to write that 2X in yellow. We know that this other side of the circle is going to be 360 degrees minus 2X. And now we can use our angle outside the circle theorem to say that our 30 degrees is equal to 1/2 our bigger arc. So that's going to be 360 minus 2x minus our smaller arc, 2x. I'm going to distribute that 30 through there. So that's going to be 180 minus x, or 30 degrees is equal to 180 minus 2x. We're going to go ahead and subtract 180 from both sides to get a negative 150 is equal to a negative 2x, or x is equal to 75 degrees.